All right, this is 6-7 exponential functions, and we're going to be evaluating and graphing an exponential function. So let's write down what that definition is. A function where the variable is an exponent. So I'm going to code this with symbols. I'm going to go variable ABC because anytime we're talking about a variable, that's a letter. Let's go ABC. And an exponent, I'm going to write X with a little a. So that I remember it's the exponent. So the variable, the letter, is in the exponent. So an exponential function is a function where the variable is an exponent. Okay. So we've got y equals 2 to the x. And y equals 1/2 to the x. Scroll. Below that, so this top line is y equals 2 to the x. So go ahead and put a little arrow that shows it goes with y equals 2x. I'm going to highlight a couple of things that are important for you guys to note. The main thing is that it has a y-intercept of 0, 1. So put that on your graph. The y-intercept of 0, 1. So y to the 2 raised to the x power has a y-intercept of 0, 1.
Oh, wait, no, it says 2. Right there.
One thing I also would like you guys to note is that this does not cross the the x-axis. So it does not get negative. You look, the top line never goes down and dips below, so it's never negative. And let me tell you why. If I plug a -2 in for x, we would get 1/2 squared, or 1/4. If I plug -4 in for x, I would get 2 to the -4, which is 1/2 to the 4th, which is 1/16. So I can plug as many negative numbers in as I want to that function, and I would never get a negative answer. Okay. Let's look at what happens when I put a negative in front of my 2 to the x. So this bottom graph goes with y equals -2 to the x. So it's going to have a y-intercept of 0, -1.
Bless you.
And it is never going to be positive. Where this one on top dips up, this one is going to dip down. Okay, so y equals 1/2 to the x power. let's make a note of where the y-intercept is. Once again, it is here at 0, 1. So this line is here. As long as our base is positive, we are always going to have a positive range. It's never negative. And then the one that is the negative version of that, you have negative 1 to the x power over 2. We take our y-intercept and we change the sign to get this one down here. And he is never positive. But look how instead of starting really negative and coming and opening up, this one, it like opens up backwards. It's awesome. He's the opposite one. The opposite way. Okay, so we're given a table and an equation, and we're going to identify if it's linear or exponential. So we're going to take a little look at A here. If x is equal to 0, I get out 1. If x is equal to 1, I get out 3. If x is equal to 2, I get out 9. If x is equal to 3, I get out 27. This is very similar to the way y equals 3 to the x power operates. Because if I plug in 0 for x, 3 to the 0 is 1. If I plug in 1 for x, 3 to the 1 is 3. 3 squared is 9. And 3 to the third is 27. So this is definitely exponential. So you guys have to find the pattern. It's hard as fuck. Okay, y equals 3x. Is that linear or exponential? Do I have an exponent at all in this problem? No. So it's got to be linear. There are no exponents other than 1. The number 1. Okay, you guys take a peek at these two charts and rule and tell me whether they are linear or exponential. All right, you guys. If we plug in 0, we get 1. Plug in 1, we get 2. Plug in 2, we get 4. Plug in 3, we get 8. Is that linear or exponential? Yeah, if it were linear, the difference between each of the y values as you increased 1 would be the same. And in this case, the difference between 2 and 1 is 1. The difference between 2 and 4 is 2. The difference between 4 and 8 is 4. So if the difference between consecutive terms is not the same, it's definitely not linear. So what would this exponential function possibly be? Let's try 2 to the x, since we got 2 when we plugged in 1. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. So this is definitely exponential. What about B? Is that exponential or linear? Exponential, it's got an exponent. It's got this little x in the exponent, so it gets to be exponential. Hard one. Suppose 30 beetles are left alone in a bin. We're done with beetles, we'll just leave them in their bin. the population doubles each week. So when we're doubling, we have a base of 2. If somebody tells you we're doubling, go ahead and automatically put in 2 for our base. The function y equals 30 times 2 to the x gives the population after x weeks. How many beetles will there be in 56 days? So we're going to use our equation, but we're not going to put in 56. Why are we not going to use 56, Connor?
Because it says weeks.
Right. And we need our time in terms of weeks. So 56 days is how many weeks? Days is there are 7 days in each week. 56 divided by 7 is 8. So we're going to put 8 into our equation. Okay? So we're going to go 2 to the 8, which is 256 times 30. 7,680 beetles. Okay, so now you guys go ahead and give it a whirl. An initial population of 20 rabbits triples every 6 months. So it triples every 6 months. Y equals 20 times 3 to the x gives a population after x half-year periods. How many rabbits will there be after 3 years? And your hint, you're not putting 3 in the equation. Okay, so we are going to plug in 6 for x because there are 6 half years in 3 years. So it's y equals 20 times 3 to the 6th. So 3 to the 6th is 729, and we're going to times that by 20. 14,580 rabbits. Okay. So we're going to go ahead and work on graphing the function. So we got y equals 2 times 2 to the x. Remember our order of operations. When we plug in our -2 for our x, we have to deal with that exponent first. So that's equal to 2 over 2 squared, which we can simplify down to 1/2. Now we're going to plug in -1 for the x. Some of you guys were really having trouble doing this on your skills test. Plugging in the value given to you in the table or in the from the graph and plugging it into the function. So this is equal to 2 over 2. I know what that is. 1. I plug in 0. 2 to the 0 is 1. And 2 times 1 is 2. 2 times 2 to the 1, that would be 4. And 2 times 2 squared is 2 times 4, or 8. So go ahead and get your chart values, then throw them on your graph. So we got -2, 1/2. We have -1, 1. We have 0, 2. We have 1, 4. This is where we swoop up, and 2, 8. Oh, I missed it. Okay. So plug the numbers in. Make sure you go ahead and get the fraction value out. Don't be afraid to use fraction. When you put it on the graph, you're just going to have to estimate. Estimate about 1/2. Estimate about 1/3, 1/8. Okay, guys, take a second and try this with 1/2 times 2 to the x. All right, so when you plug in the -2, you end up getting a 1/2 squared. That is 1/4, and 1/2 times 1/4 is 1/8. 1/2 times 2 to the -1, the 1/2 stays, and the 2 to the -1 becomes 1/2. That negative exponent bumps you down to the bottom. And then 1/2 and 1/2 is 1/4. 2 to the 0 is 1, and 1 times 1/2 is 1/2. 2 to the 1 is 2, and 1/2 times 2 is 1. And then 2 squared is 4, and 4/2 is 2. So we're going to go ahead and graph those points. Remember, we're estimating our fraction. So if I have -2, 1/8, that's going to be really close to 0. -1, 1/4, that's going to be a little bit further up from 0. 0, 1/2, that's a little bit easier to estimate. 1 and then 1, right there. And 2 and 2. So we have, it gets really close to 0, swoops up.
Swoopity swoop.
Can I grab him?